Okay, everybody, we're back and we are doing a quick review of the concept of power from our grade 11 course, and even back in grade 9 you started talking a little bit about power. It's an interesting word. In English we often use it to mean more than, or something different than what we use it for in physics. So to start off with a reasonably good definition, power is the rate of change of energy. How quickly energy is changing. And so if we write that sort of in a little formula style, it's the change in energy, and of course to make it a rate we have to compare that change to a time. The rate of change means comparing how energy changes over a period of time. So this is a simple, basic way to express it. Now also remember that power can equal something. It can equal any change of any kind of energy. So if we look at this, perhaps we have a change in kinetic energy. Something that's moving at one speed suddenly changes its speed to another. Well, if we look at how fast it changes its speed, and we compare the change in its kinetic energy, as I'm writing here, over time, that's one way to figure out the power that's involved. We also have power can be a change in gravitational energy over time. This would be changing in your height. And if you're near the Earth's surface, changing your gravitational energy would be mgh2 minus mgh1 compared to the time it took. So a change in height could also be used to calculate a power. You can also consider this to be a change in energy as you apply a force through a distance. And of course that means we'd be talking about work over time, which would be Fd cos theta divided by the time it takes. So you're pushing something up a ramp or something along those lines. In grade 9, you even learned that power can be the voltage times the current in an electric circuit. Right? Now, it's a little bit, these look like so many different things, it's hard to see how they're all related. But if you look at the units, if we play a little bit with the units, we can actually discover that they all actually are doing the same thing. So just for fun, let's play with some units. Let's go over here and look at how a change in kinetic energy could result in power. Well, remember, we have the Newton. Let's just remind ourselves of what our complex units are, which is a kilogram meter per second squared, because it's mass, remember, times acceleration. And then we have the unit of energy that we use, the joule, and that's if you apply a Newton of force. So for energy, the joule is a unit of force, the Newton, kilogram meter per second squared, applied by a distance or through a distance, which is another meters. And so for the joule, it's a kilogram meters squared per second squared. And then our friend the watt is basically a joule divided by time, right? It's energy, which is joules, divided by seconds. So that's kilogram meter squared per second squared divided by seconds. And if you use your invert and multiply rule, meters squared per second cubed. So you see this one is the watt, and we have the joule, and we have the Newton. This is why unit cancellations don't work very well in physics, because it's hard to cancel a Newton or a joule or a watt when you don't know what they're actually made of inside. But now let's look at our examples. For a change in kinetic energy, we're talking about, if you look at kinetic energy, 1/2 mv squared. Well, a mass is measured in kilograms, and v squared is meters squared per second squared, because it's meters per second squared. So that's giving us a joule when we do energy. And of course, if we divide that by a second for joules over time, we get kilogram meters squared per second cubed, which is the watt. So a change in kinetic energy is a change in joules over a time, producing the unit for power, which is the watt. And if I do the same thing looking at MGH, well, MGH is a mass, so it's a kilogram, multiplied by g, which is an acceleration, meters per second squared, multiplied by an h, which is meters. And this gives us kilogram meters squared per second squared, which is our friend, the joule. So that's a kind of energy. And if I just simply divide the joule by seconds, again, I get the unit for watts, kilogram meters squared per second cubed. So there's watts again. So a change in gravitational energy, a change in kinetic energy, you can see how we keep ending up with watts. And even if we look at it's a little bit trickier, but if we look at the power equals V times I with electricity, voltage times current, well, remember, what we're hoping to figure out is that we get watts over here on this side. We want this to work out to the unit for a watt, which is a kilogram meters squared per second cube. And if it works out, then this would be a fair statement. While voltage is basically a measure of how much force there is, it's force on a particular charge in, say, an electric circuit on an electron. And the current is kind of a measure of how fast that electron is moving. It's like a speed. And of course, a force is a Newton, so we could write in kilogram meters per second squared for the Newton, and then we would be multiplying by a velocity, which is meters per second, and lo and behold, if you do the multiplication, you get kilogram meters squared per second cubed. So this is also a watt. So you can see how all of these things look very different, but they're all ways of describing power. And so power is simply the rate at which work is done. So let's do some very easy examples just to kind of practice. We won't worry about the electricity one. I threw that in for fun, just so you can remember some grade 9. So let's take a bicycle is moving at 3 meters per second. How much power is required? Actually, how much power is not a very, I don't like saying it that way because it implies that power is a tangible thing, but it's not. It's a rate, right? So it would be better if you would ask yourself in English, you would say, what is the rate of energy usage? You wouldn't say, how much rate is there? So I'm going to say, what is the power? That kind of makes more sense. What is the power required? How much just doesn't seem to fit with power. It goes with energy. How much energy? What is the power required to change the bicycle's speed, change its speed to 8 meters per second in 2 seconds? Because remember, it's how fast you're changing energy compared to time. So we're going from, let me just check there, from 3 to 8. So in this case, the power would be a change in energy, and it would be a change in kinetic energy because the object is a bicycle that's moving. And so it would be the second energy minus the first energy. And of course, we can do a little bit of factoring out here. Oh, I guess I would have had to tell you the mass of the bicycle too. So to make this a good example, let's go back and say a 40 kilogram bicycle. My mistake. A 40 kilogram bicycle. But you can see how really it's just a function of the change in speed. So it's 1/2 of the 40 kilogram bicycle. Oh, wait a minute. I'm going too quickly now, and I'm leaving stuff out, aren't I? The math threw me off. We forgot something here, didn't we? And if you noticed it, then good for you. What we forgot is the bottom of our expression. We wrote the change in energy on top, but we forgot about divided by time. And that's kind of critical because that's what power is all about. So let's go back and fix this up. The change in kinetic energy divided by the time. So we still have time on the bottom here. But it's easy to figure this out. It's 1/2. The mass is 40 kilograms. And we have, we're going from 3 up to 8. 3 meters per second up to 8 meters per second. So our second speed is 8. 8 meters per second squared minus 3 squared. And that's still all over a time, and the time was 2 seconds in the question. So now we can figure it all out. It's 20 in here, and then we have 64, take away 9, divided by 2. So that's going to be equal to 10 times what's in the brackets, which is 55. So 550 watts of power would be required to change your speed from 3 meters per second to 8 meters per second in 2 seconds, if you happen to be 40 kilograms. And that's how it can be done. And then we'll do another quick example of how we could use it for height. Let's say you lift an object upwards. Here's an object, it's on the ground, it's 10 kilograms, and you lift it up, up to here, at a height of, let's say, 15 meters, still 10 kilograms, right? So, and you did that, so maybe I should write it out. You lift a 10 kilogram box 15 meters up in 3 seconds. What is the power? How quickly have you used up this energy? So what have you done? Well, power is the rate of change of energy, in this case gravitational energy divided by time, which would be the mgh in the second position, take away the mgh in the first position over time. And again, it's mass, which is 10, times g, which is 9.8. And I'm going to factor that out. And then it's h2. Now in this case, your h1 would be 0 because you're using that as your benchmark. We always do that with gravitational energy on the Earth's surface. And we're going to do this in 3 seconds. So we have to do a little bit of math here. And we have 98 newtons. 10 times 9.8 is 98 times 15. And then we're going to divide that by 3. And it turns out that the power comes out to about 490 watts. Right? Right. Another way to think of that, it's the same idea. Another way to think of that is if you're lifting a box, then the force you apply is equal to the weight of the box in order to lift it at a constant speed, which is mg, right? And so work is force times distance. Work is the change in energy. And so the force would be mg, and the distance is the height at which you are moving the object. So if you put in here 10 times 9.8 and the height to which we moved it, 15, you see how you get the same expression that we have over here. And then power is work over time. So if you put that number here and you divide it by time, you end up in the same place as we did over here. Another way to think of lifting, but we were doing a couple of examples just to give you the hang of it. And that's all I'm really going to say right now about power.